I think it's time to start.
Yes. Hello, everyone. Thank you again for joining us, and welcome to the second session of the first day of the Arab Oil and Gas Academy Internship Program. This is again Nihal Munir. I'll be your moderator for the day. As the last session, we will be only reading questions on the Q&A tab and YouTube Live. We won't be looking into the chat part. I just have one thing. Please keep the questions on the Q&A part only relevant to the technical content of the lectures. Any other questions you have about the internship, please do it. Please send that on the Facebook just to, I'll be able to filter the questions and we can give like a relevant lecture at the end. Without any further ado, I would like to introduce our speaker for the day. Engineer Khalid Saleh. He joined Schlumberger in 2013 as a wireline field engineer with a primary focus on open hole logging portfolio. In 2016, he moved to Data Processing Center as a petrophysicist to provide multi-domain projects in Egypt, North America, land, and Gulf of Mexico offshore. In 2020, he became the wireline petrophysicist and acoustics domain champion in charge of evaluation services, business development by providing technical consultancy to clients in Egypt, Sudan, Jordan, and Lebanon. Engineer Khalid, over to you.
All right, thank you very much for this introduction. So good morning, good afternoon, wherever you guys are based. So today we'll be talking about open hole logging through wireline. It will be an introduction session. We'll be going through the first phase, why do we need to log? And then we'll be going through the different services that we provide. And then later, I'll just go through an overview on how to do a basic formation evaluation in order to resolve the different parts of this exercise. So the agenda for today, we'll be going through briefly through the E&P life cycle. Why do we need to logging? What's logging, and the different types of logging environment. Then will be followed by the different services. I've grouped them into families, let's say, nuclear, resistivity, nuclear magnetic resonance, sonics, and acoustics, wellbore imaging and dip meter, and finally, through pressure points and fluid sampling. Towards the end of the presentation, I'll be giving you an overview of the formation evaluation on TechLog, which is one of the softwares that is provided through Schlumberger through SS, which is Software Integrated Solutions. All right, so E&P life cycle is divided into 4 phases: explore, appraise, produce, and develop. So explore starts with a very basic, let's say, part of this exercise where we acquire the surface seismic, and through the interpretation and the processing of the surface seismic, we reveal what's there beneath on the subsurface. Through exploration and surface seismic, we build our model, and using this model, we start to select where to drill. Based on this exercise, we drill our well, and then we start the logging phase. So logging typically falls under the appraisal section of this E&P life cycle. Once we fully appraise the well and do the formation evaluation, we start to case the well, perforate, and then produce. Once we drill multiple wells and start production for a certain period of time, we start to look how to develop the field through laterals or direction drilling in order to increase the recovery of the reservoir that we're dealing with. So in a nutshell, logging or wireline logging in specific falls under the appraise part of the EMP life cycle. So what's logging? Logging is the process of measurement where we lower different tools when we require different services into the wellbore. So logging can be done on different parts or different services through, first of all, wireline, whether through the wireline cable or TLC, which stands for tough logging condition, which basically happens through drill pipes. So what happens in this case is that we connect our wireline tools into the drill pipes, and then we acquire wireline logging. This is typically very common when we have problems in following the cable wireline logging. The third type of wireline conveyance is tractor, where we basically lower our tools on a mechanical tool in order to help us reach and start the logging process. And this is very typical in horizontal wells. The second type of logging is through LWD, which stands for logging while drilling. And in this case, we lower our LWD tools on drill pipes, and they are basically logging while the well is being drilled. Another type of wireline logging is through bit, and this is a new addition to Schlumberger, where we had acquired the slim tools. These tools can be drilled and can be actually logged through the drilling bit. So this can also be done through wireline. And finally, the stick line, which is a type of service that we can provide to our client. It's very basic in terms of measurements, but still it's very good into application when it comes to case tool environment. So the logging process. Logging, basically we acquire different services, let's say different data at different depths. And through the acquisition of these different tools at different sensors, we start to build up the data response versus depth. So in this slide, I'm showing a schematic or the logging process where we start at, let's say, time 0 at the very bottom of the well near the TD. In this time, we have actually powered up the tool, where we basically started to acquire the data. And then after a certain period of time, as the tool moves up the well, we start to get multiple points. These points are being logged simultaneously. So we acquire from each and every tool and each and every sensor the type of log that we need to acquire. And then finally, through this different sampling rate, we can connect these dots in order to show what we typically see in a wireline log, which is the log response for the formation. So wireline logging is done through a cable where we lower our tools into the borehole. These tools can be combined differently. A very basic or a very common type of tool is the triple combo, or even sometimes we go with a quad combo. Of course, there are different services and different types of tools that can be integrated or combined, but for simplicity, we'll be focusing more on the triple combo, and then we'll be going through the advanced type of tools later during this presentation. So logging can happen into different phases of the well. Let's say the life of the well. So we can acquire open hole logging when there is just the borehole being drilled, and typically in the borehole there will be drilling fluid. So there is no casing and there is no cement. And this is our primary focus for today, which is open hole logging. The second type of logging is the one that happens when there is a casing and a cement into the borehole. So this is the case where we start to check the integrity of the cement and do a typical CBL, VDL, which is cement bond log and variable density log. Later in time, once we evaluate our reservoir through the open hole logging and then runs the cement, we typically expect to perforate. And this is the third phase of the well, where we start to identify our pay zones or reservoir, and then we decide which type of perforation that needs to be done. Once we perforate the well, the fluid inside the reservoir start flowing all the way up to the surface. So these are the different phases of the logging environments. First of all, the open hole, and then followed by the cased hole when we run cement and the casing. And then once we identify our pay zones using open hole interpretation, we start to go to the third phase where we start to perforate. So open hole logging or formation evaluation is a very critical part of the appraisal phase of the E&P life cycle, because basically it identifies the main pillars, whether to continue developing the field or just go and plug and abandon and then go look for something else somewhere else. So typically open hole logging, it's important because it resolves primarily 4 pillars of the open hole formation evaluation. Starting off with the lithology description, what type of lithology do we have, type of formation, shale, sand, carbonate, dolomite. And then it goes to the next phase, which is the reservoir porosity. How much porosity do we have, which should represent the storage capacity of the reservoir. How much fluid that this reservoir can hold in order to be economically producible. And once the reservoir porosity is identified, we go to the saturation or the hydrocarbon saturation. So we identify the porosity, and then we see how much of this pore spaces is filled actually with hydrocarbon and how much is filled with water. The more water we have, the less economical this reservoir would be. The higher the hydrocarbon, that's our primary target. Once we identify the hydrocarbon saturation, we need to go and see the type of the fluid that we have, whether it's gas or oil. And this has different techniques in order to identify the fluid type and sampling. So basically, the wireline logging is done, and it's important because it identifies the lithology, reservoir porosity, saturation, as well as the fluid type. In order to do this, we need to identify, as a result, our typical outputs of the formation evaluation, which is the gross section of the pay zone. And then we identify the net rock, which is typically the rock volume, like let's say, for example, sand minus shale. And then we identify the net reservoir, where we basically apply a second cutoff in order to identify how much pore spaces that we have. So once we identify the net reservoir, we go to the net pay, where we integrate and use a third type of cutoff, which is the saturation. Why is this important? It's very important in order to identify a very important part when it comes to appraising the field, which is the original oil in place equation. So original oil in place equation typically is shown on the right-hand side, where there's a factor, and this factor is multiplied by porosity, 1 minus SW, which represents the hydrocarbon saturation, multiplied by the area in acres, and then multiplied by H, which is net thickness. This is all divided by beta oil, which is a formation volume factor. So as you can see, 3 main inputs into this equation, which is typically the H, which is the net thickness, 1 minus SW, which represents the hydrocarbon saturation, and porosity, comes directly from open hole logging interpretation. And this shows why open hole logging is very important. So as I said, we need to start answering a few questions in order to identify if we have a success and we actually would start to develop the field or not. So starting off with shale volume. The first main pillar for a complete and successful formation evaluation is to identify the type of shale, as well as identify how much volume of shale that we have. On top of that, we need to identify the type of lithology, whether it's sandstone, dolomite, limestone, as well as resolve the porosity of the reservoir to see how much pore spaces that we have, which should represent the storage capacity of the reservoir. Once we identify the volumes and the reservoir porosity, we go to the third phase, which is a hydrocarbon saturation, where we identify how much of this pore spaces is actually filled with hydrocarbon and how much is filled with water. Once we identify the saturation into the reservoir, we need to see if this fluid, let's say for example, it's an oil well, how much is movable and how much is bound. And this goes to the fourth type of uncertainty that we need to have and we need to address. How much of this fluid is movable and how much of this fluid is bound to the grain size. Once we identify the movable fluid, we need to understand the reservoir structure in order to design our completion string. And this typically happens when we acquire wellbore imaging as well as we acquire acoustics in order to understand how the stresses are being distributed into the formation. Once we identify the reservoir structure and design the completion, we go to the next step, which is the reservoir pressure points and fluid sampling. And at that time, we start to actually acquire the fluid sample that is downhole at in situ conditions. So by this, we need to take a very close look onto this slide because I'll be going through each and every section. And then at the end, we'll be combining all of these things in order to show a complete set of picture on how to evaluate the reservoir. So starting off with the first part, which is shear volume. So open hole logging suite or open hole logging services are typically divided into different families, starting off with the nuclear family, where we acquire the response of any nuclear radioactive material. And this can be divided into sub 4 categories: natural gamma ray, bulk density, neutron porosity, as well as elemental spectroscopy. The second type of family that we have is resistivity, where we have basically lateral log, which works in water-based mud, induction, which works in oil-based mud, and triaxial, which is a very important type of resistivity tool that we log, and this comes into play when we evaluate laminated sand. The third type of family that we have is the nuclear magnetic resonance, where we identify basically how much movable fluid that we have into the reservoir. And this would come into play into the third phase of this exercise. And the fourth type of family that we have is acoustics. I'm not talking about just secondary porosity estimation. I'm talking about wellbore stability, core pressure prediction, fracture identification, as well as anisotropy. The fifth type of service that we have is the wellbore imaging and dip meter, where we basically show how the formation would look like as if we have taken a core and we see how the formation downhole would look like, as well as see the dipping of the formation itself relative to the north direction. And this is very important when it comes to understanding the structure and understanding the positional environment where the reservoir is actually located. The sixth type of family we have is pressure points and sampling, where we basically acquire the reservoir pressure, identify mobility, as well as acquire fluid sampling at in situ conditions for later analysis, such as PVT, which stands for pressure, volume, and temperature. Finally, we can also acquire sidewall core, and this comes into handy when we try to understand carbonates in specific, because carbonates are very heterogeneous. In order to identify how heterogeneous is this reservoir, we need to acquire sidewall cores that can be sent later to the coring lab and do the special core analysis. So typically in open hole logging service, we have almost like 7 to 8 families. There's one family that's not being mentioned here, which stands for the wellbore seismic, but this is just out of the scope of the presentation today. But it's worth mentioning that we have an 8th family, which is the wellbore seismic acquisition. So starting off with the first family, nuclear. So nuclear gamma ray, natural gamma ray. Basically, a gamma ray tool, how it really works is that we have 3 main elements into the formation or into the nature that are radioactive by nature, which are potassium, thorium, and uranium. Due to the contribution of potassium, thorium, and uranium, radioactive material or these radioactive materials, a gamma ray is being emitted and this is called a natural gamma ray. When a natural gamma ray is emitted from the formation itself, we have into the tool crystal, which basically works when the gamma ray is being emitted from the formation, it falls on the crystal. So this crystal converts the energy of the gamma ray into electrons. These electrons are being multiplied into different dinodes. Dinodes are positively charged. So the reason why this is positively charged is to attract as much as electrons as we can, and also to multiply them in order to see an amplified or a higher signal when it comes to the data processing downhole. So typically what we have is a natural gamma ray being emitted from potassium, thorium, and uranium from the formation. It falls onto the crystal inside the tool. This crystal emits light. The light is contributing or hits the PM tube, which is the photomultiplier tube. And then electrons are being emitted that are being multiplied at different levels. And finally, we get a total amplified signal that is proportional to how much energy or how energetic is this gamma ray. So the more electrons that we have towards the end of this loop, the higher the energy of the gamma ray. The less electrons that we have towards the end of this loop, the lower the energy of the gamma ray. High gamma ray means it's more shaly. Low gamma ray represents a cleaner formation. So how does this work? So basically, as I said, we acquire gamma ray at different depths. And then by looking at the minimum gamma ray and the maximum gamma ray, we can identify where our shale zone, and then we can identify our clean zone, which should represent, in this case, a clean sand. And what's in between should represent a shaly sand. Natural gamma ray is very important when it comes to well-to-well correlation, as well as the shale computation or shale volume computation. But shale is a generic name, same as a family. But inside the shale, there are different types of clays. So how do we identify which clay type that we have? For this reason, we developed the spectral gamma ray. So spectral gamma ray works in a different technique where we basically measure the concentration or the ratios of each and every element, typically thorium, potassium, and uranium. And by looking at the ratios of thorium, potassium, and uranium, we can identify the type of clay, such as kaolinite, chlorite, montmorillite, illite. This is very important when it comes to identifying hot sand, because typically a hot sand is very rich in feldspar. And if we just rely on the gamma ray, the old gamma ray, we might be misled by the response of the high gamma ray in this case. So in a hot sand, where it's rich in feldspar, due to the radioactive material that we have in the sand, the other gamma ray would read high in count rates, which should be, as a first look, identified as shale, but in the real life, it's really sand and it's not shale. And this comes into play, especially when you start evaluating basement rocks. So spectral gamma ray uses, as I said, the three ratios, thorium, potassium, and uranium, in order to compute two outputs, which is typically CGR and SGR. So SGR is the summation or the contribution of the three elements, thorium, potassium, and uranium, all combined. This should represent the SGR. And CGR just shows the contribution of thorium and potassium. So whenever we have an overlay between SGR and CGR, we can identify and be 100% sure that it's a clean formation. It's not being rich in any radioactive material. And whenever there's a slight separation between CGR and SGR, we know this effect is just coming from uranium, and this might be actually misleading when it comes to formation evaluation. So by doing this, by just understanding the natural gamma ray and how the spectral gamma ray works, we can identify the type of shale that we have, as well as compute the volume of the shale that's there present in the reservoir. Now going to the next step, which is the lithology volume and reservoir porosity. So in this case, we have a bulk density and photoelectric factor measurement. What happens in this case is that we actually inject gamma ray into the formation. This gamma ray starts interacting with the rock that is mainly composed of the grain matrix or grain particles. And it's also in between, the fluid is actually showing also some contribution. Due to the interaction between the gamma ray as well into the formation and the fluid, some of the gamma rays are being released and come back to the tool, and some of them are being captured, where basically they're just stopped and the energy of the gamma ray is very low to reach back to the tool. Excuse me. So the gamma rays that are being captured comes into play when we start evaluating the photoelectric factor. And when the gamma rays are being emitted from the tool and back to the emitted from the tool into the formation and back to the tool again, this comes into the bulk density computation. So the bulk density computation is primarily focused on or dependent on the Compton scattering, where we start to emit gamma ray, and this gamma ray starts interacting with the formation, and then it emits the outermost, the electrons in the outermost shell, and then it's being deflected back to the tool. Typically, the energy range of the gamma ray in this regime is ranging from 75 kilo electron volt to 10 mega electron volt. That's very high. But when the gamma ray are being emitted and then they're being captured, in order for this to happen, we need to knock out the electron that's very close, or typically at the innermost shell of the electrons, typically very close to the neutron and the proton, which is the nucleus. And this acquires a lot of energy in order to overcome and knock out this electron outside. And that's why most of the energy are being utilized and being captured when this is happening. And this comes into play when we start detecting what we call the photoelectric absorption, which translates to the photoelectric factor. The energy domain or the energy level at that instant is less than 75 kilo electron volt, which is typically very low when it comes to the nuclear world, when it comes to gamma ray energies. So bulk density and photoelectric factor is acquired from a single tool. It's a pad tool, as you can see on the left-hand side, where we basically have a source, a gamma ray source that emits gamma ray. And then these gamma rays interact with the formation in the fluid, and then comes back. Some of the gamma rays come back at the near detector, which is called short space detector. And some of the other gamma rays come at the long space detector, which is far ahead from the source itself. Using these two different type of detectors and measurements, we can derive the bulk density or the rho B of the formation. At the same time, since the gamma ray is still being emitted, some of them are being captured, and the amount of or the number of gamma rays that are being emitted versus the number that's coming back to the tool itself represents how much of this energy has been lost and how much gamma ray has been absorbed, and this would correlate to the PEF measurement, which is the photoelectric factor. Bulk density, formation bulk density comes into play, and it's a very important input when it comes to evaluating the type of lithology, as well as estimating the reservoir porosity. PEF, on the other side, is a very good lithology indicator, but just bear in mind, since PEF is very dependent on how much gamma ray are being emitted and the number of gamma rays that are being absorbed, it's severely affected by any high gravity solids into the mud system. A typical and a very common type of material that really attenuates the PEF measurement is barite. So the presence of barite into the mud severely affects the PEF measurement. And this is something that needs to be taken into consideration while you start looking at or having a quick look oversight on the data that you acquire through a triple combo dataset. Now going to the third type of nuclear tool that we have or service, which is the neutron porosity. So typically neutrons, in this case, we emit neutrons at very high energy from the tool using a chemical source or an electronic source, such as a PNG, which is a pulse neutron generator. The energy typically is, at the start of the emission, is very high, and as it interacts with the formation as well as the fluid, it starts to rapidly decrease into the energy level until it reaches what we call a thermal state. So this thermal state represents how much, or shows how much hydrogen index what we have inside the formation and the reservoir. The steeper this drop into the in energy represents more hydrogen index. The more relaxed this energy drop is, the less hydrogen index that we have in the pore spaces. The reason is why we emit neutrons and how this is really dependent on hydrogen index is typically by physics, the mass of neutron is equal to the mass of the proton, which represents the hydrogen. So hydrogen is an equivalent to the proton, and due to the collision between the neutron and the hydrogen, neutron loses a lot of energy until they're being captured in the thermal state. So what happens is that we emit neutron at very high energy. They interact first of all with the borehole, and then they interact with the formation fluid as well as the matrix. And then the neutrons are being captured back onto the different sensors that we have. We have typically two sensors, the short spacing, which is very close to the source, and the long spacing, which is a bit far from the source. The reason why we have two detectors and we're not only relying on one detector is that the near detector is primarily attenuated or affected by the borehole condition, such as washouts or hole rugosity, as well as the borehole fluid. But if we have another detector that's far ahead from the source itself, then it reads more deep inside the formation, and it's less being affected by the borehole condition, and it's actually seeing what is there inside the formation. Using these two different measurements from these two different sensors, we're trying to correct for any borehole condition or effect that might be affecting the final output of the neutron porosity. So slowing down the rate is proportional to the hydrogen index. As I said before, we started very high energy, and the rate of slowing down, how much time it takes to slow down the neutron to reach the thermal state, is proportional to the hydrogen index. So hydrogen index is a quantity which should represent how much hydrogen we have per unit volume. The more hydrogen we have, the faster this energy would the slowing down rate of the neutron would be higher. The less hydrogen we have into the borehole, the slowing down rate would be very, very slow compared to high hydrogen index. Since hydrogen index or neutron porosity is primarily affected by the presence of hydrogen, which is the proton, then we say that neutron porosity measures the total porosity, which in this case, it measures any hydrogen that's there in front of the tool, whether it's coming from water, gas, or oil. So how do we interpret the neutron porosity and the bulk density in order to resolve the type of fluid, the type of lithology, as well as the reservoir porosity? So typically we plot what we call a composite plot, where it typically combines different measurements. For example, in this case, we're combining gamma ray in the first track, as well as the caliper. And then this second track represents the bulk density and the neutron porosity. So just by looking at the neutron porosity and the bulk density, we need to make sure that we have the right formation type and the right compatible scale. So typically a compatible scale is something that's being used in order to show a good visualization on how the neutron porosity and the bulk density would respond to each other. And just by looking at the plot itself, we can identify where there's an overlap. For instance, it might represent water. Whenever there is a separation between neutron porosity and the bulk density, it would represent gas. and the same goes also for oil with less separation. So what happens here is that we look at the gamma ray first, when there's low gamma ray. So typically low gamma ray is around this area, as well as at the top of the reservoir, as well as the top of this log. So we are expecting to have a clean formation in this reservoir, and this leads us to go and look at the neutron porosity and the bulk density. So typically, when these tools were calibrated and they were designed in a limestone matrix that was water-filled. So whenever there is a limestone matrix, there is limestone downhole into the reservoir and it's water-filled. All the points, let's say for example, if it's a limestone in this case, everything should be lying on this line. But if it's a sandstone matrix and it's a sandstone formation that's water filled, all the points should be lying on the second line or the first line. And if the formation is dolomite and it's rich with water filled or rich with water, then it should be typically lying on the dolomite line. So let's have a look how this would work. This is a cross plot between bulk density, which is rho b, and neutron porosity, which is n phi. So what we do is typically plot the curves that we have from the neutron porosity and the bulk density from the data set that we have, in this case, which is a triple combo. We plot these data onto the cross plot. And we see how these points would fall onto these different trend lines: dolomite, calcite, and quartz. So first of all, any water-filled, as I said, the tools were built in limestone formation that was water-filled. So typically I should be expecting an overlap when there is limestone into the formation and it's water-filled, provided that we're using the correct compatible scale. In this case, the compatible scale is ranging from 0.3 to minus 0.1. Later, we plot the other part, which is shows a separation between neutron porosity and bulk density. And this is typically a very good signature for gas presence. The more separation that we have between neutron porosity and bulk density, the more gas that we have. And this is typically called the balloon effect. So as I said, since this is limestone, if it was water filled, it should have line over this this trend line. But since due to the presence of gas, now the hydrogen index is typically lower in gas compared to water, and that's why the points start to deviate and move towards the top, where we typically expect to have lower porosity, since the total porosity is dependent on the hydrogen index, and gas has a low hydrogen index, as well as have low or less dense material or bulk volume, since gas is less dense by nature compared to any fluid. So typically gas, any points in the gas or any gas in the formation would start to deviate from these three different lines all the way to the top towards this region. All right, so now going to the dolomite. When we plotted the dolomite that was water filled into the cross plot, they became the overlay onto the dolomite line, which is mainly showing dolomite formation that's water filled, since it's falling on this dolomite line. And then finally, when we are plotting shale, which is being presented by the high gamma ray, shale always fall towards the right bottom side of this cross plot. The reason is that shale is considered more dense, a little bit more dense, because of the amount of bound fluid that it contains, as well as the high porosity or high pore spaces neutron porosity, because typically shale is very rich with water, and the more water we have into the shale, the more the hydrogen index, which should represent an increase in neutron porosity. So shale typically is lying over this region of the cross plot between neutron porosity and bulk density. Finally, when we're looking at salt, such as sulfur, anhydrite, or any other salt material or formation, a very good a very good response for sulfur or salt or anhydrite is that they all share a common behavior, which is a very low porosity. It's almost like zero. So anything that is zero porosity should be considered as anhydrite or salt, unless we have a different type of measurement that confirms it might be a tight sand or tight carbonate. But for simplicity now, we need to just assume that we're dealing with porous sand or porous carbonate. But just bear in mind, if we have tight sand and tight carbonate, we would be expecting something around this area. So it should also show zero porosity, but due to the difference in density, for example, anhydrite is very dense, it's almost around 3, and salt and sulfur is like around 2.05. So the key differentiator in this case is the bulk density, the true bulk density of the formation itself. If we have a tight sand or a tight carbonate, we'd be expecting zero porosity to fall around this zone or this zone in case of sand, but the bulk density would change for example, for sandstone, it would be reading around 2.65 typically, limestone to around 2.71. So as you can see, by just looking at the neutron porosity and the bulk density, we can come up with different idea or more insight of the type of lithology that we have, whether it's dolomite, limestone, sandstone, if we have a water-filled sandstone or we have a gas-filled sandstone. And also if we can also identify through the high gamma ray and the neutron porosity as well as the bulk density if we have a shear effect. There's one thing that needs to be also highlighted here is that you see there's like red dotted lines or circles where you can see these lines are being broken down into different compartments. So it starts from 0, 5, 10, 15, 20, 25, etc. These represents the estimated, or let's say an initial guess of the reservoir porosity. So just by relying on the neutron porosity itself, it's a very critical part that needs to be taken care because it's misleading when you try to evaluate the reservoir. And that's why we need to use different independent measurements in order to derive and see the effect of the actual lithology as well as the fluid and identify the reservoir porosity. So in this case, for example, for this zone, the points are lying on the limestone line. And if we look at the data cluster, it will be falling around the 20 PU. So this shows that it's a limestone matrix that's water filled and the average porosity of the reservoir is around 20% PU. Another case is a limestone matrix at the bottom where we have the same trend, limestone water filled, but the porosity is reading around 10 PU. And this can be applied to dolomite, limestone, and sandstone. But what if we have a complex reservoir? So this other approach works perfectly fine when we have shady sand sequence, or we have a dolomite or carbonate, pure carbonate or pure dolomite. But it's very tricky when we have a combo of these different elements combined, like sand, shale, dolomite, anhydrite, and sometimes pyrite. So the complex the reservoir gets, the different technology we need to use in order to derive the lithology that we have. And this comes into play when we have the elemental spectroscopy. So elemental spectroscopy is basically dependent on the neutrons that are being emitted from the tool. So we have a neutron tool that emits neutron at very, very high energy. It uses an electronic source, what we call the PNG, pulse neutron generator. And this neutrons interact with the formation, and due to the interaction with the formation, the induced gamma rays are being emitted and they come back to the tool. So what would typically happen is that we emit very high energy interaction with the neutrons, with the formation and the liquid. Due to the interaction with the liquid and the formation, induced gamma rays are being emitted from whatever the tool is actually in contact with, and this induced gamma rays come back to the tool. The induced gamma rays detect and can be broken down into what we call spectrums. So the first type of spectrum that we have is the inelastic spectrum, and the second type of the spectrum that we have is capture. Inelastic, from the word itself, the neutrons hit the nucleus of the matrix or the fluid, and then it bounces back and comes back or emits gamma ray that are coming back with a certain signature. The capture spectrum is a bit different, where we basically emit neutron, and then due to this interaction, they lose energy, and due to this lost energy, they start to absorb and being captured by the elements. And then the capture elements start to emit a signature gamma ray that are being collected back to the tool. By analyzing the two different types of spectrums, the inelastic spectrum and the capture spectrum, we're able to measure more than 22 or 21 elements that are present in the Earth crust, and this can solve more than 99% of the elements that's there present in the Earth crust. This is very important when it comes to analyzing unconventional reservoir or complex lithologies that we have in, for example, here in Egypt, the Gulf of Suez. So it comes into play because we can accurately measure the clay volume directly from the tool, and then we can solve the sand, pyrite, limestone, and dolomite. And this is very important when it comes to a proper formation evaluation, because the more accurate the volumes that we have, the better the estimation of the porosity. And this would affect severely the oil in place equation calculation when it comes to reserves estimation. Another element that we also measure is what we call carbon. So carbon is typically found in any carbon-rich material. Some of them can be organic carbon and some of them can be inorganic carbon. So organic carbon are typically anything like oil, bitumen, kerosene, gas, light oil. And inorganic carbon typically comes from the chemical composition of different elements of different lithologies, such as calcium carbonate, which is limestone, calcium magnesium carbonate, which is the dolomite, siderite, etc. So what we typically happen is that we measure the total carbon that's coming into the tool, and then we remove the effect of any inorganic carbon, and the remaining is the total organic carbon. This comes into play, and it's very important and very helpful when it comes to unconventional reservoir evaluation, typically in the US land, where they have a lot of unconventional pays. So by doing this, we have primarily identified the shale volume using gamma ray and natural gamma ray, and then we have identified the type of matrix that might be there present in the formation, such as sandstone, limestone, dolomite. Even if it's a complex reservoir, we can start using spectroscopy measurement, where we can derive the lithology directly from the tool, and also get an estimate of the total porosity of the reservoir. Now it's important to go to the next phase, which is hydrocarbon saturation. So typically, hydrocarbon saturation is computed using resistivity. So we have typically two types of resistivity families. We have Latour log and induction. So Latour log works in water-based mud, where we basically have a tool that has an electrode that emits a very high output of current. This current is being injected into the formation. The deeper the current goes into the formation, the more depth investigation that we have. And the shorter the current would go into the formation, the less depth investigation we have. Typically, a Latour log is a 5 output. So it has RLA1, or let's say the shallowest resistivity is the one that's very close to the borehole, all the way up to RLA5, which is a Latour log at the depth level of 5. And this is the deepest resistivity that can be measured, and this should be representing the RT, which is the true formation resistivity of the reservoir. This is happening at multiple frequencies in order to inject current. So from physics, voltage is equal to I times R, which represents current times resistance. We know the current that we're injecting into the formation, and we measure the voltage drop between each and every point, and each and every point at each different depth of investigation. So this means that we can compute or measure the resistivity using the very simple equation V is equal to IR, voltage is equal to current times resistance. The second type of tool that we have is that, to further elaborate on this, as I said, we emit very high current output that goes deep into the formation, and they're being detected at multiple receivers across the tool body. Due to this interaction, we can estimate and measure the current or the resistivity at each and every investigation. And by measuring the voltage drop, we can see and compute the resistivity of the formation. This is a very good example where we start to see the differences and see the azimuthal response from the resistivity curve. So in this case, we have what we call LLD, which represents the very deep resistivity response coming from the deep part of the reservoir, which should be the uninvaded zone, version zone. LLS is the shallow resistivity, and LHR, it's the azimuthal resistivity. So by just looking at the resistivity curves on the log view, it's a logarithmic scale, we can see, first of all, we can identify where's our high resistivity, and this should be contributing typically to our hydrocarbon zone, but it might be misleading sometimes when we have fresh water. So fresh water is typically less, it has less chlorides, NaCl, and NaCl, since it has a chlorine atom, it has a chloride anion. It's the more chlorides we have into the water, the more saline, which means the less resistive, and vice versa. The less chlorides we have into the formation water, the higher the resistivity of the formation water, and therefore the more resistive. So sometimes we might be misled by just looking on the resistivity itself and us on detecting or trying to understand if it's a hydrocarbon bearing zone or not. So for simplicity, we'll be just looking at this and assuming that the high resistivity would represent a hydrocarbon presence, and the low resistivity would be presenting something like water in this case. By just looking at the contrast between the low resistivity and the high resistivity, we can identify easily where's our, or typically we can say that our pay zone is supposed to be across the clean gamma ray as well as the high resistivity, but it's also worth the importance to look at the neutron porosity, because sometimes if we have a tight rock where we have very low small pore spaces, typically in tight sand or tight carbonate, we might have a high resistivity profile. And this is typically happening because the neutron porosity, since it's dependent on the hydrogen index, the less pore spaces that we have, the less hydrogen index that we have per unit volume or per unit rock. And therefore, it will be reading almost zero porosity. So this zero porosity, think of it as if it's a solid. Solids, if they don't have liquid inside them, they would not easily conduct electricity. And this typically happens when we have tight sand. So in order to come up with a better visualization, we need to look at different independent measurements together in order to come up with a better insight of what we have there downhole in the subsurface. So we identify low gamma ray, and then we go from low gamma ray, look at the resistivity profile, identify where there's high resistivity and there is low resistivity, which is typically water. We can use also a baseline in order to just look at this visually. And then we just, in order to properly, or like to be a little bit certain about the hydrocarbon presence, we also need to look at the neutron porosity as well as the bulk density. The second family, or the second group of resistivity we have, is induction. So induction works in a different way. Induction works in oil-based mud. So in an oil-based mud, since we have oil into the borehole, if we have a current being emitted from the tool, the current would not flow into the formation since it's stopped, or it's not being penetrating through the formation due to the non-conductive medium that the tool is being run. And the reason is we developed an induction tool is that we use a different technique. So primary, it starts with a transmitter. It has a transmitter array and a receiver array. The transmitter array, it has a coil where we start to inject current into the coil inside the tool. Due to this injected current, a magnetic field, a primary magnetic field, is being built across this first coil. The magnetic field of the coil inside the tool in the transmitter array intersects or comes over the ground loop, what we call, which is the formation, the ground loop. And this ground loop, we would create another magnetic field into the formation itself. This magnetic field would intersect or would come into contact with the receiver array inside the tool too. And this magnetic field would start to emit and start to measure an electronic response, an electric response in the tool. So basically, we're not injecting current inside the borehole, we're injecting current inside the coils in the transmitter array and the receiver array. The current that's being emitted in the transmitter array, they go into the loop, generate a magnetic field. This magnetic field inside the tool interacts with the ground loop, which is typically the formation. And the formation, they will generate a secondary magnetic field. This secondary magnetic field interacts with the receiver coil inside the tool. When the magnetic field from the secondary magnetic field interacts with the coil in the receiver array, an electric current is being generated. The more current we have generated inside the receiver coil, the less, the more the signal is, the more signal that we have on the receiver coil, the higher the resistivity. The less signal that we have, the less the resistivity. So as I said before, we do this at different depth investigation. In this case, it's also 5 depth investigation where we acquired or we induced this magnetic fields at different frequencies. And we look at the separation between the resistivity, whether in lateral log or induction, in order to understand how permeable the zone is. So typically when there is a separation between the shallow, medium, and the deep resistivity, it's a very good indicator when we have a permeable zone. The more the data are stacked or they're superimposed or overlaying to each other, shallow, deep, and medium, the less permeable the zone. Another output also that comes out from the resistivity is the very deep resistivity. Typically in this case, it's 80-90. So 80-90, which is the green line here, it's like almost 7.5 feet inside the formation, which is very deep. So it's less likely to be affected by the invasion. And we start with 10, 20 inch, 10 inches, 20 inches, 30 inches, 60, as well as 90. So typically we assume the 90 inch is the true formation resistivity, which is RT. And this is very important to identify in order to compute hydrocarbon saturation when we come to this step later during this presentation. So what happens in thin beds? So typically if we have a clean, big sand and big shale body and big sand body, the response is more or less visualized and can be easily captured through the tool itself, whether it's lateral log or induction. But when it comes to thin lamination sand, and this is very typical when it comes to evaluating lithology, especially here in the Nile Delta, the old approach, whether it's lateral log or the induction, does not really work well. And this is a very good example. We would see the response of these formation very, very low. And this can be misleading sometimes when it comes to formation evaluation. And that's why we need to really measure different type of resistivity, which is called the triaxial. So triaxial is also an induction tool. But instead of having one receiver and one transmitter, we have transmitters at different axes, X, Y, and Z, and receivers at X, Y, and Z in order to measure the signal at a different azimuthal measurement. And by doing the full resistivity tensor, which is an algorithm that's being done into the tool itself, we can start to resolve for two things called RV and RH. RH, which represents the horizontal resistivity, and RV is called the vertical resistivity. So RV and RH, think of it as instead of having series circuit. So series circuit, if we need to identify the total resistance in a series circuit, we need to just have a summation of R1 plus R2 plus R3, etc. But if we have a laminated sand, think of it as a parallel circuit. So for identifying the total resistance in a parallel circuit, we use 1 over R is equal to 1 over R1 plus 1 over R2. So by identifying the tensor, full tensor resistivity, and by looking at the signal coming from the different azimuth, X, Y, and Z, whether coming from the transmitter or the receiver array, we can come up with the RH and RV. Using this RV and RH, we develop or we plotted using something called the tornado plot, where typically we plot the RV and RH. And using the shale point as an indicator, we can identify what we have as a final output for RV and RH. And this is very typical practice when it comes to laminated sand. So in this case, it's an example where you can see gamma ray, high gamma ray, low gamma ray. So this low gamma ray is easy to identify, and just looking at the RT, low gamma ray, neutron density, and just basic evaluation, you can identify this is just the pay zone. But when we looked at the image, the wellbore imaging, there was actually thin laminations that are being detected by the image, as well as the NMR nuclear magnetic resonance. When we resolved RV and RH, you can see initially, if we were just really dependent on the RT itself, we would see a very lax response, very low resistivity that would be misleading when it comes to formation evaluation. But when we resolve RV and RH, we can start to see that the vertical resistivity is a bit higher compared to what we see in the RT. And this, when they were tested, this came out to be producible, and it added another pay zone that was previously missed just due to the fact that we were just relying on the RT itself. So in this case, the sand or like the major sand body was already identified by the conventional Latour log, which is RT. But using the RV and RH, using the triaxial resistivity, we're able to add more pay into the reservoir through the thin bed laminations that were evident initially on NMR and images, and they were backed up by the RV when the RV and RH computation was done. If this was not available, this pay zone would be still there, but they would be overlooked, and this would represent an example of a bypassed OA. So as I said, in order to resolve for saturation, we need to understand and look closely into the resistivity. So what happens into the basic formation evaluation or quick look is that we look at the plane body, plane gamma ray, and then I said we look at the resistivity. We identify where there's high resistance and low resistance. Typically, we'll be assuming high resistance for simplicity at this level. That high resistance would represent hydrocarbon, and low resistivity would represent water. And once we identify where is our high resistive zone, we just go cross-check the neutron density and neutron bulk density in order to see the separation between them, in order to identify, for example, gas, oil. And then typically water, the points or like the data, neutron porosity and the bulk density should be overlaying. So by just doing this quick look evaluation, we can start punching the numbers into this basic saturation equation, which is typically the Archie's equation. So Archie's equation is SW, which is saturation of water, is equal to the nth square of A, which is the empirical constant, typically assumed as 1, multiplied by RW, which represents the resistivity of water at a measured temperature downhole. And then it's divided by phi raised to the power of m, which is the porosity of the reservoir raised to the cementation exponent that's usually estimated or assumed as 2. And then we have RT, that's the deep resistivity that we can directly get from the tools itself, whether it's AT90 in case of induction, or RV in case of thin bed laminations, or RLA5 in case of Latour log. So by doing this, we can start to estimate and compute how much water saturation that we have. And using the SW, we can subtract 1 minus SW in order to get what's remaining, which should be contributing to the hydrocarbon, whether it's oil or gas. But the question is, how do we get RW? So RW, typically, we can get it from different methods, but the most common method, if we have a water zone, we go to the water zone and then using the Art's equation by taking log to both sides. So taking log to this side and the log to the other side, we can derive this basic equation by assuming SW is equal to 1. So it's log RT is equal to minus M log phi plus log ARW. So if you have a closer look at this equation, it represents what we call equation of straight line. So where we have y is equal to mx, which m represents the slope and x is the independent measurement, or dependent measurement in this case, and y is the intercept. As I said before, a is assumed to be 1, so typically this is just log rw, which means in order to transform this into an equation of a straight line and plot it, we need to plot it on a log-log scale. So what we plot is the log RT. This is log-log scale. We plot RT on the y-axis and phi on the x-axis. And the slope would represent the what we call the m, and the point of intercept, which typically happens at log phi equal to 0, would represent the RW. And this is only applicable when we have a water zone. So we made 2 assumptions. First of all, we made an assumption to A, which is equal to 1. And then we went to the water zone, assumed that it's 100% water filled, and there's no residual oil, or there's no oil in this part of the reservoir. And then we plot the points, and based on the slope itself, we can slope and intercept, we can assume the RW. This is the first approach. In case if we don't have a clear water body into the reservoir, it might be found somewhere a little bit deep or a little bit shallow. It's still applicable, but it's not the best approach. Still, people use it in the industry, but this is just provided that they don't have a water zone near or inside the reservoir that they have. But just bear in mind that if you have a look and you just see the TVD section of the reservoir, which is the true vertical depth of the reservoir, if the zones are pretty close together, let's say like 100 meters, 50 meters away, the resistivity of the RW would still be a good approach or a good starting point. But just bear in mind, it's not the best approach. The only valid, or let's say that the only best technical approach to estimate RW is to collect a fluid sample from downhole, water sample, send it to the lab, and just measure the RW at the lab itself, and then you can just input this RW into the saturation equation that you're using, for example, in this case, which is RC equation. So back to this equation. So since we have RW, whether it's coming from the Pickett plot, which is the one that I was discussing a bit earlier today, or whether you have a direct input coming from a measured water sample collected downhole and being sent to the lab, we can have the first input into this equation. We have A as 1, we have porosity using the cross plots between the neutron porosity and the bulk density. We have M assumed as 2, N is also assumed as 2, and RT coming directly from the tool, 80, 90, RLA 5, or RV. Then we can start to calculate SW at each and every point of the reservoir, and then we subtract SW from 1 in order to compute how much hydrocarbon saturation that we have in place. Since we identified the hydrocarbon saturation, after identifying the volumes that we have, we need to now identify how much fluid is movable, how much water is movable, how much oil is movable, and how much gas is movable. In order to do this, we need to look at NMR data. So NMR is a nuclear magnetic resonance, where we basically have a magnetic field being generated or being induced into the formation through the tool. So we have a permanent magnet in the tool that emits a magnetic field, a constant magnetic field and pulsed magnetic field. This magnetic field would orient the hydrogen index into the space. So when the magnetic field, the permanent magnetic field is being in contact with the hydrogen index, they start to spin into the vertical direction, in this direction. And then we have a pulse magnetic field that's being also emitted from the tool. And this would orient or flip the hydrogen index from the vertical axis to the horizontal axis. The time the hydrogen would take from this horizontal axis all the way back to the vertical axis represents the what we call the NMR measurement, which is the relaxation time. By measuring this relaxation time, we measure how much the amplitude is coming back to the tool and the time it takes. Typically, the more hydrogen we have inside the reservoir, the more the amplitude would be, and the longer the time, the less hydrogen index, then we have a lower amplitude and less time. So the area under the curve would represent what we call, once we invert this amplitude time domain to what we call a T2 distribution, is this kind of distribution. The area under this shaded curve or like shaded area, the green line, the green area would represent the storage capacity of the reservoir. And this is a lithology independent porosity. By looking at this spectrum of T2 distribution, we can identify multiple things into the reservoir when it comes to movability of the fluid. First of all, by looking at the very high peak towards the later time of T2, we can identify the free fluid porosity and how much free fluid that we have into the pore space. By looking at the shorter T2, which typically comes at a very short T2 distribution around 0.3 to 3 to almost like 10 microsecond, we can identify how much bound fluid that we have. This bound fluid can be subdivided into small pore spaces or small pores, as well as the capillary bound. So capillary bound, typically they will not flow, and they're just very hard to flow. Small pores comes into play when we identify and start to look at tight lithologies such as tight sand or tight carbonate. So by just looking at this T2 distribution, that's an output from the NMR measurement, we can identify and easily identify and see how much bound fluid we have versus how much free fluid. The free fluid would contribute to the movable fluid that's easy to move. So typically what would happen is that once we perforate, typically anything in front of this zone would easily flow. And anything, if we have a lot of this into the reservoir that we have, then it needs further stimulation in order to start producing the reservoir and put it in production. So there are different applications for NMR or neutron magnetic resonance. So as I said, first of all, it provides a lithology independent porosity. So you can just use this porosity and compare it directly to the core. They just show a one-to-one correlation. It's a very good thing once we don't have a core data acquired or being taken from the well, and we need to estimate the core porosity. And this is a very good and very representable storage capacity when it comes to formation evaluation, which is the NMR porosity. Second thing is identifying the pore spaces that we have, how big the pore spaces are. The bigger the pore spaces, the more it would lie towards the higher end of the T2 distribution. The smaller the pore spaces, the more it would lie towards the left-hand side of the T2 distribution. So the more this peak comes to the right, it represents more free fluid and more more pore spaces. The more this peak would come towards this side of this T2 distribution, it would represent small pore spaces and more bound fluid. And it's also worth mentioning that another application of NMR is that estimating the irreducible water saturation. Since we can identify easily how much movable fluid that we have, we can also identify the irreducible water saturation when it comes to understanding what would be the residual water into the formation in order to estimate the water cut for the reservoir when it comes to production. Since we're measuring the NMR porosity, it's also worth mentioning that we can derive and compute two types of permeability equations, SDR and Timur quotes. These permeability curves can be a very huge input when it comes to understanding the phases that we have into the reservoir. So typically, what a reservoir engineer would like to have is they would like to have a porosity, the reservoir porosity, plotted versus permeability, whether this permeability is coming from a correlation that they have developed into the field, or a measurement that's being acquired through a log or a service, or another type of source of permeability can be the core permeability. But core permeability is a bit expensive. It's quite expensive to do NMR permeability estimation into a full bore core. And that's why most of the clients, they would prefer to run NMR, or if they have a very solid knowledge onto the field and the phases of the field does not really change a lot, then they can just develop a permeability equation that they can use later in order to derive permeability. Using the permeability and the porosity, the reservoir engineer would start to classify the reservoir into phases. Let's say clean sand, silty phases, shady sand, sandy shale, in order for them to better assign their field and reservoir properties when it comes to dynamic simulation and when they change the static model to a dynamic model. Here's an example of how NMR is actually showing a comparison between how much bound fluid and how much free fluid. So this very right track, it shows the T2 distribution that was shown before. By just looking at the T2 distribution, the points or like the peaks are coming actually at the very late part of the T2 distribution, which should be just directly looking at this, estimating that, or like assuming that this is free fluid, compared to another case when we have most of the peaks coming towards the shorter time window of the T2 distribution, towards the early stage of the T2, which shows more bound fluid. So this is just as a quick indication while logging, you can just, while real-time QCing the job, you can identify if this reservoir is actually bearing the fluid and how much of this fluid can be movable. So just by barely looking at these two distributions, I can say this is a bad reservoir and it needs further simulation to be produced if there is hydrocarbon. And this is a good reservoir that can be easily produced just right after perforation. So now we've identified almost 60% of the reservoir evaluation. So we started with shale volume, computation, lithology, and as well as porosity. And then we went to saturation or hydrocarbon saturation. And then we identified how much of this fluid can be movable just looking at the NMR and looking at the permeability. Now it's time to look at the reservoir structure and the completion design. So acoustics. Acoustics is primarily focused once we emit a waveform, or we emit a sonic waveform that's being emitted from the transmitter. It vibrates. As the transmitter vibrates, it keeps propagating into the formation, into the borehole fluid, and then it comes into the formation. And then at a certain angle, it starts to deflect back and it goes back to the receiver. Once we get the signal back to the receiver, we can start to measure three main outputs of acoustics, which are typically compressional slowness, shear slowness, and stony slowness. So compressional slowness comes at a very high, or like very short time after emitting the transmitter, followed by shear and then followed by stony. So a typical response, if we have the three signals coming from the formation, is that we get the compressional arrival first, and then we get later in time the shear arrival, and then a little bit later in time after shear, we get the stony. So it goes compressional, shear, and stony. But how the waveforms really propagates into the formation. So in case of a compressional, think of it as if you have a hammer and you just keep knocking on the matrix itself. So the waveform propagation is actually going down into the lithology or the formation itself. But for shear, we're actually knocking onto the lithology from the left-hand side to the right-hand side from the sideways, and we're just bending the formation as if it's like looking like a snake in this case. So for compressional, the waveform propagation goes from up till down, and for shear wave, it also goes up and down, but in this case, the waveform also goes into an S shape, let's say, and it just keeps moving the particles into this direction instead of compressing the particles in this direction. So compressional, from the word itself, it compresses the formation, it squeezes the formation itself. Shear, as if we're just breaking the formation, we're just trying to knock the formation and try to break it down into different layers. So as I said, we have a transmitter that at time zero, at the beginning of the transmission itself, it starts to emit a pulse, a wave that keeps going into the mud, and that's why we have a mud wave. As the mud wave itself interacts with the borehole wall, in this case, at time microsecond, 70 microsecond, we start to have a refracted compressional and refracted shear. So as I said, the compressional, since they would reach faster, this means it's ahead of shear. So shear is a bit late and compression is a bit faster. And then once we reach what we call a critical angle, then we get head waves. So a head wave, the compressional head wave would start to go back to the tool faster. And that's why we measure it faster in time compared to the shear, because shear would be taking a little bit more time to go back to the tool. So this is typically what happens into the sonic or acoustics acquisition when it comes to transmitter and arrays. So we have a transmitter that emits very high energy pulses. They travel through the borehole fluid, and then they interact with the borehole wall. Once this interaction happens, we start to get refracted compression and refracted shear. Once these waveforms, or once these signals reach the critical angle, they come back again to the receiver, and that's how we detect compressional slowness, shear slowness, as well as stony slowness. So for this to happen, we need to have different receivers at different depth investigation. So typically the greater the distance between the transmitter and the receiver, the more depth investigation the tool would cover. The less the distance between the receiver and the transmitter, the shorter the depth investigation. So we're really interested into getting the most signal coming from the deep receiver, but we are also bound by anything that comes into the borehole due to the effect of mud or borehole rugosity. And that's why we need to measure at multiple depth investigation in order to remove the effect of the borehole as well as the mud. So as I said, in time domain, the compressional would arrive first, and then later in time, the shear head wave would arrive later. And then after a certain period of time after shear, we get the stony. So what typically happens is that we need to combine all these measurements, since they're coming at different detectors, detector 1, receiver 2, receiver 3, 4, 5, 6, 7, 8, in order to measure and get the final output of stony slowness or shear slowness or compression slowness. We need to do what we call STC processing. So STC stands for slowness time coherence, where we basically plot time versus coherence. Coherence is the data density, which is typically in red. The red the color, the higher the confidence in the signal. The blue the color, the less confidence that we have in the signal. So we plot coherence versus time and also versus slowness. As I said, in terms of time domain and slowness domain, we should be expecting, in terms of slowness and time, we should be expecting compressional, shear, and then stony later in time, and also later in terms of slowness. So this cross plot or this snapshot is if you're looking at this histogram, or like, let's say, view of this coherence time slowness from the top side. So if we look at from this top side, we're looking at the time versus slowness, which should be representing this. The bigger the amplitude of these peaks, the more the bright spots will be, which is typically in this case red spots, which shows high confidence. The less peaks we have here around this area, then we have these blue spots. So by just looking at this coherence map, we can identify the compressional slowness, which is in this case, for example, it's reading around 60 microseconds per foot. And then we can identify the shear slowness, which is reading around like 105 microseconds per foot, which is in this case. And then later in time, we can identify the shear slowness, which is around 200 or 190 microseconds per foot. And we just do this for each and every depth in order to come up with what we see typically when it comes to array acoustic waveform. This is just the basics of acoustics. So these are the main pillars when it comes to the advanced applications of acoustics. In order to do these advanced applications, we need to properly measure compressional, shear, and stoning. So a very good application when it comes to acoustics is understanding the borehole geology, understanding if we have bedding, if we have fractures, if we have breakouts to the formation that can be correlated and can be integrated with the wellbore imaging. So this is a very good example application when it comes to carbonate evaluation, for example. Another good example when it comes to geomechanics, when we're trying to predict the drilling induced fractures or estimating the pore pressure prediction for drilling the well, and designing where to perforate and how to perforate, understanding the stresses inside the wellbore. And then we can use this in order to come up with a mechanical earth model that can be used with the geomechanics engineer in order to develop a full picture of the stress regimes, as well as design how to complete the well later during production. So in this case, in this presentation, I'll be just going briefly over geomechanics and wellbore geology. There are a bunch of other applications such as rock physics when it comes to fluid substitution, when it comes to inversion of the seismic. And then there's another application when we develop synthetic seismogram, when we try to enhance our surface seismic data using the borehole acoustics by deriving the synthetic seismogram. And typically, very good application, a very common application is the well integrity and casing integrity, which is, as I said before earlier, during the early life stages of the well, we have open hole, and then we case the well, we run casing and cement. And in order to understand the integrity of the cement itself, we need to run what we call a CBL, which is Seaman bond log, and a VDL, which is a variable density log. Later during this internship, my colleague, Maria, she'll be just going through the case hole evaluation, and she'll be talking much or touching more base with the CBL and VDL measurements. For the time being, I'll be just going through the geomechanics and wellbore geology. So when it comes to geomechanics, in order to understand geomechanics is basically or primarily designed and built on understanding the stresses inside the borehole, and also by looking at the density. But in order to understand the stresses, we need to quantify them. And the way we quantify stresses is by looking what we call shear anisotropy. So anisotropy, from the word itself, if something is called isotropic, this means that in the X, Y, and Z directions, all the properties, the physical properties, are equal together. For example, in this case, I would be reading in this direction 100 microsecond per foot, and in this direction 100 microsecond per foot. So this is what we call isotropic. But in anisotropic, we have a change in the magnitude of the physical property that we have dependent on the direction where we measure it. And this comes into play, especially when it comes to evaluating stresses. So due to stresses, let's say, for example, I'm stressing the formation from this direction, I'm compacting the formation much more from this direction, I should be expecting to read a different slowness compared to this relaxed direction. So if we're applying stresses by just looking at this difference in slowness in the different directions, let's say, for example, in X and Y direction, I can easily identify there's a stress regime here that needs to be quantified. But stresses does not only primarily happen, or like anisotropy does not primarily happen due to the maximum horizontal stress and minimum horizontal stress. It can also happen due to fractures, as well as bedding, such as shale. In order to identify if the anisotropy is really related to stresses or the effect of fractures or bedding, we need to start integrating the acoustic and anisotropy results with wellbore imaging that will be shown later in order to see if it's really it's the effect of bedding, which comes into shale, that will be evident on the wellbore imaging as very laminated sand, thin laminated sands, or thin laminated layers, and whether it's just coming from the stress regime that we have in place downhole that's creating a maximum horizontal stress and a minimum horizontal stress. So this is an output of the shear anisotropy. What typically happens is that we measure shear in two different directions. We measure it in the X and Y direction, which is shown as here. The difference between the slowness from the X direction and the Y direction would show a separation. This separation also contributes to an energy difference between the both waveforms that coming back to the tool. Once we see there is a change in energy between the X and Y direction that's being shown here as a result of this separation, we can identify what we call a fast shear azimuth. Fast shear azimuth is the direction at which the fast shear, which is the fast shear slowness, is propagating. And in drilling induced fracture, or typically when we have anisotropy, we need to start fracking the well into the direction where we have the magnitude of the fast direction. So in order to start fracking the well, where we create a permeable pathway into the formation, we need to know the direction of the stresses, which is being already identified, and also the azimuth of this fast shear azimuth, of this fast shear slowness. Typically, the slow shear slowness or shear azimuth would be 90 degrees from this, because we're measuring two components, the X and Y, that are 90 degrees apart. So why do we need to know the direction of the fast shear? So direction of the fast shear is very important in order to understand the direction of the fractures, because the fractures would primarily go in the direction of the high stresses. And also it helps us to estimate and know or visualize the productivity of the well itself. Since the fractures, or like the production, would follow the fractures itself, which represents the high permeable pathway, then if we have more stresses and we have more fractures into the reservoir, we estimate that there is more permeable zones, and this should be contributing to more productivity. Another application for shear anisotropy is that avoiding sand production and also optimizing the perforation, directing the perforation into the direction of the fast shear, or the high S-max. So in this case, if we identify the direction of the minimum stress, and as a result of this, it will be the maximum stress in this direction. If we perforate in the direction of the minimum stress, we mean that we damage the rock, which means that there is a very high probability of having sand production problems during later in time during production. So in this case, we need to orient our perforation into the direction of the fast or the maximum stress. Same goes with us designing the perforation itself. When we start to frac the job or do the fracking job, we need to understand where's the fast shear azimuth direction in order to frac into the direction of the maximum horizontal stress. And in this case, it will be in this direction, since it's orthogonal or 90 degrees offset from the minimum stresses. If we frac in these directions, the amount of penetration of the frac itself would be very limited, and it would be very small compared to if we frac into the direction of the maximum horizontal stress. Another application for acoustics is Stoney. So Stoney waveform is a waveform that propagates onto the borehole itself. It does not really go inside the formation. So compression is typically, compression and shear typically gets refracted and then reflected back to the tool once they get into the formation. But Stoney, due to the nature of the Stoney waveform itself, it's a borehole waveform, which means that it typically moves along the borehole wall. It does not really go inside the formation compared to compressional and shear. So compression and shear really goes inside the formation, but Stoney, they really propagate along the well borehole. And this comes into play when we try to identify what we call open fractures. So if we have a waveform that propagates across this borehole all the way up, when it comes to an open fracture, a series of reflection and refraction will be happening across this plane as well as this plane. So by looking at these reflection and refractions from the stony waveform that goes into the borehole wall, we can see what we call a chevron pattern. So a chevron pattern represents the reflection and the refraction across the borehole, and by just looking at the chevron pattern itself, just barely from the stony waveform, we can identify and easily see what we call open fractures. Open fractures is a very good thing that we need to have in a reservoir in order to make sure that we have a permeable pathway for the fluid inside the borehole or inside the formation to flow and produce. This is a very good example where we show a comparison between what we detect using the fast and slow shear. So we see this fast shear slowness and the slow shear slowness. By looking at the difference between these two together, we can identify there's a difference. There's a difference in terms of microsecond per foot. And this is correlating to what we see in terms of energy. So we see a very huge energy difference between these two compression or these shear slownesses. And this would represent an anisotropy happening at this interval. But also looking at the stony waveform and by identifying the fractures, we can also see that there is a fracture coming from the stony waveform represented by this purple shading. And once we were looking at the FMI images, the images itself, we can identify that there are drilling induced fractures here. And these fractures were actually shown on the image, and they were also shown on the sonic, which means that these fractures are not closed fractures or cemented, but in fact, they are liquid-bearing fractures, which means that they're open fractures and they could contribute to production later in time. So this shows an integration between acoustics and images and how we can come up with different pieces of information on the reservoir itself as structure, as well as the stresses in order to design our completion and understand the structure where the deposition environment of this field happened. So now going into the next step, which is the wellbore imaging. So wellbore imaging, it's a pad tool. It's a tool that measures or injects current into the formation. And this injected current comes back to the tool body where we measure how much current is coming back. And using this current, it's using the same resistivity approach. V is equal to IR. So we have 190 buttons. These buttons act as transmitters. So we have 192 transmitter into the single tool that are being divided into what we call 4 arms. 4 arms. There are, if you look at the top section of the tool itself, it has 1, 2, 3, 4. So these arms are like forming a cross or like a plus sign. And each arm has a pad, what we call a pad, and what we call a flap. These pad and flap orientation are being done in order to maximize how much current we inject into the formation in order to maximize the image that we can acquire downhole through wellbore imaging. So this is the output of a wellbore imaging tool, an FMI log, for example, which stands for full bore microimager. And this is what we can see actually into the core itself. You can see there is a very strong correlation between what we see downhole using FMI or wellbore imaging in general, and what's there actually into the nature. So it's for the geologist, it's like looking for an outcrop of the core of the rock itself. And this is a very good way to visualize what's happening down there by just looking at what we can come out with in terms of dipping, how deep the formation is, as well as the contrast between the colors. We can easily identify the structure of the reservoir, as well as any geological events that might happen that can be correlated to what we have in the deposition environment and stratigraphy. So another output from FMI or wellbore imaging is dip meter. So dip meter is actually showing how tilted is this layer or this formation compared to the horizontal axis, in this case, which is the north. So what we have is a sinusoid wave, which is a sine wave. we have, as I said, we have 4 arms: arm 1, arm 2, arm 3, and arm 4 in the 4 directions. So arm 2 would be presenting the north, arm 3 would be presenting east, south, west, and then back to north. So think of it as you have a full bore core, like you have a cylinder and you just cut it from this side, and then you just overlap this onto a white on a table, and then you can see the signature of the waveform. So typically, if we have a laminated, a dipping formation, we should be expecting a sine wave. The way we interpret this sine wave in order to identify the angle at which this layer is dipping is by looking at the tan theta, which is the theta is between the horizontal axis and the vertical axis, which is in this case. So tan theta is equal to the vertical, or like the opposite of this triangle divided by the adjacent, which is in this case 6 divided by 12, and tan minus 1 theta is equal to 6 over 12 is equal to 27 degrees. So by just doing the very simple calculation, we can get, first of all, the angle at which the dipping is, which is 27 degrees in terms of magnitude. And now we need to understand in which direction. Is it tilting towards the north, east, south, or west? In order to see this, we need to see the trough of the sinusoid. So a peak is something what we consider in a sinusoid wave or a sine wave, which is the positive part, and a trough, which is the bottom part. So we see the bottom parts. In this case, since it's coming onto the pad 1, which is oriented towards the west, this means that in this direction, or this angle, or this layer is dipping 27 degrees in terms of magnitude, and it's oriented towards west, which is coming towards almost the third quadrant of a circle. So if you have a circle, north, east, south, and west, if we have a 270 degrees, which is typically at west, then coming at this direction into the west side, it would present 270 degrees, and this would represent the direction, the azimuth of this dipping. By just looking at this, we need to identify 2 things: the trough, which would represent the direction, and the difference, or like the tan minus 1, the difference between the vertical section of the triangle and the horizontal section of the triangle, in order to identify the magnitude of the dipping itself. In this case, it's 27 degrees. So by looking at the different images that we can have, these are 4 different wells: well 1, well 2, well 3, well 4. By just looking at the image itself, the geologist would start to visualize what's really happening down there, whether we have vugs, whether we have laminations and compactions, whether we have fractures, whether we have anticline, syncline, all these kind of structures and deposition environment. By integrating and understanding or visualizing what happens downhole with images and acoustics, we can design and see how to complete the well, and also understand how to estimate how the production can be optimized using the stresses that we can compute into the borehole and the reservoir. This is the same example as I said before, so it's just showing how the integration would work. So the sonic and image, they just go hand in hand when it comes into structure analysis and deposition environment interpretation, as well as understanding the stresses when it comes to production and designing how to produce the well or reservoir. So by doing this, we have identified the reservoir structure and completion design by integrating acoustics and wellbore imaging, and then we'll be going now to the final stage, which is the reservoir pressure points and sampling. In this case, in order to acquire a pressure point in sampling, we need to lower pressure sampling tool, which is typically a tool that has a vacuum inside, and then it has a probe, what we call an inlet probe, that can allow fluid to go inside the formation. And then once we create a drawdown, which is a negative pressure, then we can identify and measure the reservoir pressure itself inside the formation. So this is very important when we start to appraise a well in order to understand the expected reservoir pressure. Reservoir pressure represents how the power of the reservoir itself, and the higher the pressure, the more the reservoir can be easily flown through natural production. It can naturally produce. The less the pressure, this means that we have to start looking for different ways to produce, such as, for example, ESP or sucker rod, etc. Also, through pressure point identification, we can develop what we call pressure gradient. So pressure gradient gives us an insight on the type of fluid that we can have. We can have gas, oil, and water. And also by looking at the pressure point and the drawdown that we make, we can estimate the mobility, which is equal to K over mu, where K represents permeability and mu is the fluid viscosity. So mobility is directly proportional to permeability, and it's inversely proportional to viscosity. On top of that, we can also acquire downhole fluid samples for PVT analysis for pressure, volume, and temperature in order to understand the type of fluid or hydrocarbon that we have in place. So as I said, we can look at the gradients at from different wells at different reservoirs, and looking just by the gradient, which is typically the pressure points are being plotted at depth versus pressure log view. And by looking at the gradients itself, we can identify the gradient of water and identify the gradient of gas. Through the intersection between the water gradient and the gas gradient, we can identify the gas water contact as well as the gas water contact in this reservoir. So from the pressure itself, we can estimate two things: the contacts, which is the intersection between the trend line of gas and the trend line of water. And also we can identify the mobility of the reservoir, and we can also identify the fluid type that we have in the reservoir. So here's a schematic or a brief schematic explaining how we start measuring pressure. So for pressure to be measured, we need to create a negative pressure inside the tool. We need to make a delta P. This negative pressure is typically happening due to the vacuum that we create inside the tool. So what typically happens is that we go to the formation that we need to test or we need to measure the pressure for. We put the tool in stationary mode, and then we inject or insert what we call a packer. This packer comes into contact with the formation. So this is the formation and this is the borehole itself. And this probe now is completely in contact with the formation, which makes a seal, a complete seal. And the only communication now that will be happening is coming from the formation itself all the way inside the tool through this flow line. So once we have the piston at position 0, for example, then we start to create a drawdown. We start to move the piston inside the tool in order to create a negative pressure. So negative pressure starts to build up at this vacuum. So once we reach to this certain position, we start to go to what we call the drawdown limit. This drawdown limit is the time where we start to stop the piston itself and wait for anything from the formation to come inside the piston or the vacuum itself. So typically what would flow from the formation into the piston to the vacuum itself, in this case, would be the embedded fluid. It would not be the formation fluid, the version fluid, because it's a very small compartment or a very small volume that we actually move into. And it's typically around 20 centimeter cube. In this case, we are just assuming that whatever response is coming from the formation deep inside is the same as what we have in the embedded zone. We wait for a certain period of time, and then what happens is that we stop the piston, as I said, and later we start to get what we call a formation response. Once this formation response stabilizes, which is the pressure versus time, once this is stabilized, this would show the expected formation pressure in this reservoir. So anything under this, the area under this curve, under this, let's say we have another line, this line extended a little bit more. anything lying under this zone is contributing to the mobility. The bigger the area under the curve, the higher the mobility, which means the higher the permeability. The smaller this area under the curve, which would contribute to less permeability as well as less mobility. So this is typically how we measure pressure. We make a negative pressure inside the tool. We have the formation coming, or like the fluid coming inside the tool, and then we measure through a gauge or a sensor inside the tool. And then once we stop the piston, we start to see any effect coming from the formation itself. And as a buildup, this pressure buildup starts to rise and stabilizes at a certain period, at a certain pressure. This would be contributing to the formation pressure in PSI. So by getting different pressure points at different depths, so this is depth versus pressure, we get different points at different depth, we can get the trend lines of the different fluids that we have, such as water, oil, or gas, and then by connecting or intersecting trend lines together, we can get the contacts of each and every fluid, for example, gas, oil contact, or oil, water contact. So these are typical values for the oil and for the gradients that we have for gas, oil, and water. But now for sampling to happen, we need to start pumping at a very high rate instead of just relying on the very small chamber or the very small volume that we have, which is 20 centimeter cube in terms of pressure points. We need to have bigger bottles or bigger flow lines in order to get what we need in this case, which is the virgin fluid. So we're using the same probe, same type of tool, exactly the same, but the only thing that's only added to this is another set of tools above it, which has a bigger flow line. It has a pump, literally a pump, where we start pumping and try to clean the formation, like the filtrate, the mud filtrate into the invaded zone. And then once we reach to a stabilized flow, we can start getting what we need to have in place, which is the oil coming from the very deep inside the formation, which is the virgin zone. So the more we pump, the cleaner the sample will be, because we're basically removing a lot of filtrate that's coming inside the invaded zone. And the better the analysis, the better the quality of the sample would be. So this fluid sample, since they're being pumped all the way up, they're being dumped into the tool. And then once we reach to an agreement that this is a clean sample, and now we're getting less contamination from the mud filtrate, we start to collect the fluid samples, the oil or the clean fluid sample inside bottles. These bottles are also inside the tool itself. They're shown here in the schematic. And these bottles are being collecting the fluid samples at PVT conditions, which is the pressure and volume, pressure and temperature reservoir in situ conditions, in order to be sent for PVT analysis. So they preserve the fluid properties at the in situ conditions, pressure and reservoir pressure and reservoir temperature, for the proper analysis for PVT. So by doing this, we have identified our volumes coming from, starting from shale, lithology, and then going to saturation of hydrocarbon, identifying if we have a movable fluid or not, and then we go to designing and understanding the structure in order to complete the well, and then finally we start to get the fluid sample that is typically, in this case, oil or gas. And this is the primary objective of open hole logging. So this is just a basic overview of formation evaluation. So let's say it's like a cheat sheet, for example. In order to start doing a formation evaluation exercise, you need to identify a low gamma ray, which should be presenting a clean zone, typical reservoir. And then we look at the resistivity. If we have a low resistivity, it's possibly wet. If we have a high resistivity, it can be two things. It can be hydrocarbon bearing zone, or it can be a tight zone. So in order to identify this, we need to check the porosity. If we have a low porosity, it's likely to be tight, which is not pay, and which is not a pay zone. And if it has a high porosity, then this high resistivity is actually contributing or coming as a result of fluid that's very resistive, and this is a possible pay zone. Once we identify our pay zones using this simplified workflow, we can start our quantitative analysis using different softwares that's there in the market, which is one of them is TechLog, that's being provided by Schlumberger through SIS, Software Integrated solutions through TechLog. If you have a TechLog version that you can use, you can just create a project. You just go under the Petrophysics tab, and you can go to Quanti-Elan. Quanti-Elan, it has 4 steps. These 4 steps are in sequence, and they have to be done in sequence. So we start with what we call initialization. Then once we finish this, we go to Quanti-Elan. And then once we're done with this, we go to combine models. And then once we're done with this, we go to processing. So these has to be done in sequence. Once these steps are being done using the data that you acquire in open-hole logging, you can come up with what we call as a post-processing or the final view of the formation evaluation, which is shown in the at the bottom here. To have a closer look of this, so typically what we're expecting is to identify the shale volume, which is considered here as V clay. And then we also need to identify the lithology, which is the lithology in this case, which is elite, the type of clay that we have, and quartz, and how much fluid that we have on top of fluid, which is in this case gas, oil, and water. And as well as identifying the porosity of the reservoir, as well as the saturation, because these V shale, saturation, and porosity comes into play when we try to identify and isolate how much sand or how much gross sand we have. And this is done through identifying and using the 3 outputs from post-processing. Typically, we have V clay, porosity, and saturation. These 3 outputs coming from formation evaluation are being used, and by applying certain cutoffs, we can identify what represents the rock. So for presenting the rock or using or getting the rock as the reservoir is being evaluated, we need to apply a cutoff on V shale. We need to say, okay, if the V shale is greater than this value, which is, let's say, for example, 0.5, then anything higher than 0.5 V shale is considered shale, and anything below that, it's considered clean zone. Once we identify the rock, we apply a second cutoff, which is representing reservoir. And in order to compute the reservoir thickness, we apply a cutoff on porosity. So let's say we have a porosity unit of 20 pu. Anything greater than 20 pu is considered as reservoir. Anything below that is considered non-reservoir. And then once we need to identify the pay zone, which is the thickness, the net thickness, which is a primary input when it comes to original oil-in-place equation, as I've shown before in the beginning of the slides, we need to apply a third cutoff. And this third cutoff comes to saturation. So we have 3 types of cutoffs that we need to apply to identify rock, reservoir, and pay. So first of all, we identify rock by applying a shale volume cutoff. And then once we identify the rock, we apply another cutoff using porosity in order to identify reservoir. And then once we identify the reservoir, we apply a third cutoff, which identifies the pay. And this pay thickness, instead of having this big cross section or like this thickness as a reservoir, now it just came to this producible fluid that can be contributing to the total production later in time. And this is the depth or the thickness that's being used into the original oil-in-place equation. So these are some references and some useful links that can be handy when it comes to understanding log interpretation, looking at the catalog of the wireline services that we can provide, as well as having a more practical insight on the theory, whether to open hole logging or cased hole logging. Thank you very much for today, and I hope you enjoyed it. Thanks.
Thank you so much, Engineer Khaled, for the very dense and very informative presentation. For everyone, we got like lots and lots of questions. I gathered as many as I could, and I'll be sending them to Engineer Khaled, and he will be answering them. So thank you so much for joining and tuning in today. You can always go back and rewatch the whole webinar on our YouTube channel, so you get, better focus if this was too long for you. One more thing, please stay our Facebook, we will be announcing few regarding